My name is Ravi Kumar. So today I am here to explain you to a vapor reheat cycle. So vapor reheat cycle problems today I am going to explain. Okay. So first I am taking a first problem. An ideal reheat cycle utilizes steam as a working fluid. So steam at 100 bar. See, they given steam at 100 bar and 400 degrees Celsius temperature. Steam at 100 bar and 400 degrees Celsius temperature is expanded in the high pressure turbine. So first pressure turbine is high pressure turbine and expand it up to 15 bar. Expand it up to 15 bar. After this it is reheated to 350 degrees Celsius. After this it is reheated to 350 degrees Celsius at same 15 bar. At same 15 bar pressure, and then it is expanded to low pressure turbine to a condenser pressure of 0.5 bar. Okay, so this is the given data. So with the help of this given data, I have to find out thermal efficiency of the cycle and what is the steam rate. Okay, what is the steam rate of the cycle we have to find out. Okay, so first I have already written a TS diagram of this. See, TS diagram, this is 1. So 1 to 2 is your high pressure turbine. It is expand from 100 bar to 15 bar, 100 bar to 15 bar. Again it is reheated at the same pressure, means that's why I have written here P2 is equal to P3. Okay, at the same constant pressure it is reheated to 350 degrees Celsius. Okay, then from P3, it is a low pressure turbine. It expands to how much? It is expands to 0.5 bar. It is expand to 0.5 bar, then it enters to a condenser. So this is a turbine, high pressure turbine, and this is low pressure turbine. CL PT, low pressure turbine, and this is high pressure turbine. So next here it is a work done by pump. So 5 to 6 is a work done by pump, and here it is heat rejected, Q out, and here it is heat addition. There are two heat addition, one is reheat, other one is boiler. Okay, so we'll see how to find out what is the formula of efficiency. So what is the formula of efficiency? So thermal efficiency formula. So thermal efficiency is equal to work done by turbine minus work done by pump divided by Q in. See, in some problem you will clearly specify that you can going to neglect the work done by pump. If they given work done by pump, you can neglect this work done by pump. You need not to consider for thermal efficiency. So again you can write this work done by means high pressure turbine plus work done by low pressure turbine minus work done by pump divided by Q in boiler plus Q in reheat. So we'll see what is a work done by high pressure turbine. So work done by high pressure turbine is, so this is 1 and 2 is a work done by high pressure turbine. So we can take it as H1 minus H2. Next, work done by low pressure turbine is H3 minus H4, low pressure turbine. Next, work done by pump. Work done by pump is this 6 and 5, so we can take it as H6 minus H5. Next, Q in boiler. So Q in boiler, or we can directly take Q in boiler. Okay, Q in boiler is what? H1 minus H6. And Q in reheat. So is H3 minus H2. Okay, see, I'll solve this problem with the help of HS diagram, or we're going to call Molière chart. Okay, so with the help of Molière chart, I am going to solve this problem. Okay, so first point is what is the input pressure and what is the input pressure on turbine, input pressure of turbine and as well as the temperature. So input pressure of turbine and temperature is 100 bar and 400 degrees Celsius. Okay, so how to place a 100 bar and 400 degrees Celsius temperature. Okay, see here, this is your Molière chart. Okay, this is your Molière chart. You can observe this is a saturation line. See, one dark line is there. It is a saturation line, and this side will be having a enthalpy, and this side will be having a entropy. Okay, and the next you can observe here 0.95, 0.9, 0.85, 0.8, 0.75. These are the dryness fraction. Okay, dryness fraction value, and you can observe on the saturation line, you can observe 0.01 bar, 2 bar, 3 bar, so on, and then you can observe at the top of the Molière chart you have a pressure. Okay, so these are the pressure, and then you can observe this curve. Okay, this type of curve, and at this point you can observe the temperature, means 800, 700, 550, 400, so on. Okay, you will be having a temperature, and similarly you will be having a temperature up to 50 degrees Celsius. So usually we'll consider this chart, and if it is a superheated, we'll consider above 100 degrees Celsius. Okay, so now we can plot this 100 bar and 400 degrees Celsius. So how we can plot 100 degree and 400 bar, 100 bar and 400 degrees Celsius. Okay, see, this is your 100 pressure. This is your 100 pressure, and 400 degrees Celsius is here. This is your 400 degrees Celsius. Okay, see, I'll draw a line along the 100 bar. See, you can draw a line along the 100 bar line up to where? Up to 400 degrees Celsius. See, at this point, 100 bar and 400 degrees Celsius are intersecting each other. So I'll call it as a point number 1. Okay, I'll call it as a point number 1. Then from this point number 1, I'll draw vertically downward line. See, I'll draw vertically downward line up to where? That is another point. So you can draw vertically downward line up to where? So you can draw vertically downward line like this up to where? So what is the next? Is again they given it is expanded in high pressure turbine up to a 15 bar. So now I have to look at the 15 bar pressure. See, here you have a 15 bar pressure. Okay, see, up to 15 bar curve you have to draw vertically downward line, means up to here you have to draw vertically downward line. See, this is your point number 2. Okay, this is your point number 2, and this one is point number 1. After this, along the 15 bar curve, the reheat taking place up to a 350 degrees Celsius. So along the 15 bar curve, you have to draw curve up to a 350. So at this point, this 350 degree and 15 bar curve is intersecting here. Okay, 350 degree and 15 bar curve is intersecting here. So I'll take it as this point number is 3. Okay, so next is again I have to take, here you have a 0.5 bar condenser pressure. So up to 0.5 bar condenser pressure, you have to draw vertically straight line. See, this is your point number 3. From the point number 3, you have to draw vertically straight line up to where? Up to 0.5. See, this is your 0.5 bar. So up to 0.5 bar, you have to draw a straight line. So this is your straight line. So this is your point number 4. Okay, so this is how you can plot the things in the Molière chart. Now I have to find out the enthalpy. See, how to find out the enthalpy? How to find out the enthalpy? See, from the point number 4, so you have to draw horizontal line up to where? Up to this enthalpy. So this is enthalpy. See, here it is 2400 and here it is 2500. So you have a 5 digit in between. So means 1 digit is equal to 20. Means 2400, and here it going to get 2480. So you have to write what is the H4. See, here it is the H4. So you can write this is 2480 kilojoule per kg. Okay. So next I have to write H3. Where is the H3? See, this is your point number 3. Okay, this is your point number 3. Again, I am going to draw horizontal line. See, I am going to draw horizontal line up to where? So up to here. So this is your H3 point, horizontal line. Okay, so means 3100, 3120, and this is 40. Okay, so next this H3 is 3140 kilojoule per kg. 40 kilojoule per kg. So next I have to look at the point number 1. See, this is your point number 1. This is your point number 1. Okay, so point number 1, you're going to get 1 second. So point number 1, 1 second, 100 bar. So this is your 100 bar and this is your 400 degrees Celsius. Okay, so 400 degrees Celsius, so you're going to get around 3200. So this is your 3200 kilojoule per kg. So next I wanted to find out H2. Okay, H2 from here, see H2 from here you'll get around 2690. So H2 will get 2690 kilojoule per kg. So this is your Molière chart. That's all about the Molière chart. So now I am going to solve the problem. So I'll just write here. So what is a H1? 3200 kilojoule per kg, and what is a H2 is 2690 kilojoule per kg, and H3 is 3140 kilojoule per kg. Next H4 is 2480 kilojoule per kg. So now I have, see, H1 and H2 I have, then H3 and H4 I have, and I have H1, I have H3 and H2. I wanted to find out H6 and H5. How to find out H6 and H5? See, H6 and H5 you have to find out with the help of steam table. So with the help of steam table you have to find out the H5 and H6. H5 you can find out and H6 you can find out with the help of formula. See, this is a pressure table. So this is a pressure table. Okay, so I have, they given 0.5 is a pressure. So here you can observe 0.05, you can observe 0.05, and then you can observe here 0.5 is a pressure. Okay, so at the 0.5 I have to note down. So which bar I have to note down? So which enthalpy? See, H5 is at this point, means at this point it is a HF. Okay, means at this point you will be having a fluid. So this is HF, means H5 is equal to HF at 0.5 bar. At 0.5 bar. So how much you will get? See, this is a 0.5 and then you will be having a HF here. Okay, so you have to look at the vertical downward line. So you will get 340.6. So HF 340.6 kilojoule per kg. So how to find out H6? So you have a formula, work done by pump is equal to VF into PB minus PC. So what is a VF? Again, VF at 0.5 bar. So VF at 0.5 bar is what? 000103101. Okay, so that I have to write here. So 000103101 and PB. So PB, what is the PB value? You will be having a 100 bar. 100 bar means you have to convert that into a kilopascal. So 100 bar into 10 to the power of 2 minus, what is the condenser pressure? You will be having a 0.5 bar. So minus 0.5 into 10 to the power of 2. So you'll get work done by pump is, see, 100 into exponential 2 minus 0.5 into exponential 2 into 0.0010301. So you'll get work done by pump is 10.5. So kilojoule per kg. So this is your work done by pump. So okay, so next, with the help of work done by pump, you know that work done by pump is H6 minus H5. So I have work done by pump is 10.25. So H6 I don't know, I have to find out. And then H5, how much you got? H5 you'll get 340.6. So minus 340.6. So you'll get H6 is plus 340.6. So how much you got? 350.85. 350.85 kilojoule per kg. So now your efficiency is work done by turbine. So work done by high pressure turbine plus work done by low pressure turbine minus work done by pump divided by Q in boiler plus Q in reheat. So what is the work done by turbine? H1 minus H2 plus H3 minus H4 minus H6 minus H5 divided by H1 minus H6 plus H3 minus H2. So we can substitute now all the things. So H1 we have 3200 and 2690. 3200 minus 2690 plus, and then H3 we have 3400, 3140 and 2480. 3140 minus 2840 minus H6 we have 350.85 minus H5 we have 340.6 divided by, so H1 is 3200 minus H6 is 350.85 plus H3 is 3140 minus H2 is 2690. So if you solve this, you'll get 3200 minus 2690 plus 3140 minus 2840 minus 3550.85 minus 340.6 divided by 3200 minus 350.85, close the bracket, and I'll just open the one more bracket, then plus 3 I'll open the bracket, 3140 minus 2690, close the bracket. So you're going to get around into 100, you'll get 24.24% approximately. See, this is your efficiency. Next is SCC, means steam rate. See, steam rate is MF divided by work net. Okay, so this MF should be in kilojoule per hour, kg per hour. So here they given only one unit, so that's why I'm considering 3600. And work net means work done by high pressure turbine, low pressure turbine minus work done by pump. So you'll get 3200 minus 2690 plus 3140 minus 2840 minus 350.85 minus 340.6. Okay, so this we have to solve. If you solve 3200 minus 2690 plus 3140 minus 2840 minus 350.85 minus 340.6. Okay, so 799, 3600 divided by answer, so you'll get around 4.5. Okay, 4.5 is kg per kilowatt hour. Okay, so this is SCC. Clear? So this is the problem. So this we have to understand very carefully. Okay, how to take the reading. So this is the thing. Okay, thank you.